Hi, everyone. Thank you so much to Randall for asking me to come give you a talk on the X-ray and UV impacts and probes of exoplanets. I am a professor at Arizona State University, but I did want to mention that I'm also spending part of my time here at the Center for Astrophysics, where I am right now. So those of you who are at the CFA probably recognize my office. So I just wanted to put that out there because I haven't met many of you yet. And I'm here on the third floor of P building, if you ever want to chat about any of this. So another thing I wanted to say is that I am also the PI of a couple of missions that are very complementary to the things, to Arcus's capabilities. One is a funded CubeSat mission called Sparks, which is due for launch in at the middle of next year. And another one is a mid-X mission called UV Scope, which it's a concept at the moment to be proposed in the next round, but it's complementary in the sense that it goes from Lyman alpha, so the far UV, to the optical, so through the near UV to the optical, all in one shot, doing spectroscopy. And there's a lot of synergies that while preparing this talk, I realized how good it will be together. All right, so there's really a lot of things one could do with X-ray, simultaneous X-ray and UV spectroscopy, far UV spectroscopy. So I actually don't have time to talk about all of it. So I'm going to focus on what I think are the two most urgent bits of research topics with respect to exoplanets. And one is the impact that the far UV and the X-ray have on heating and chemically modifying the planet's atmosphere. And this is important not just for those high energy wavelengths, but in order to interpret the transmission spectroscopy that we do at other wavelengths. So even at JWST wavelengths and at the Habitable Worlds Observatory wavelengths, understanding this high energy context and environment of these planets is quite important in interpreting all those spectra. Another is that the UV and X-ray provide their own probe of layers of the atmosphere that we cannot access through other wavelengths, primarily the exosphere and the very most upper regions of the planet's atmosphere. So I know we have a diverse group of people with interests here, so I just wanted to make sure that we're all caught up on what transmission spectroscopy is, and this is one of the leading ways in which we study exoplanet atmospheres, and we can study their composition and dynamics through transmission spectroscopy, where the planet cuts in front of the star, and the star essentially backlights the atmosphere, and different wavelengths probe different atmospheric layers, as I had mentioned. And when you have spectroscopy with good enough resolution, as Arcus does, you can also study the dynamics of this atmosphere and look for escaping gases. Now, we often don't think about stars. We don't envision stars. You guys probably do, given your X-ray and far UV inclinations, but most people don't really think about stars at these wavelengths and what they actually look like. And so I wanted to show you this nice movie of a rotation of our sun taken from SDO, the Solar Dynamics Observatory, where the optical image on the far right is probably something of what you're used to. But if you go towards shorter wavelengths, the sun really looks quite different. And it's where you get increased levels of activity and homogeneity, inhomogeneity, I should say, at these higher energies. And this becomes really important when thinking about transmission spectroscopy, because we know, even at JWST wavelengths, right, that the stellar variability strongly impacts what we can measure and how well we can measure it, and can in fact mimic certain signatures that we, certain things that we're looking for in a planetary spectrum, which is not actually in the planet atmosphere, but is in fact coming from the star. So I wanted to, as you think forward towards how you're going to propose and work through observing plans, think about the activity induced variability that might happen for all that will happen. I can guarantee that it will happen for the exoplanet transmission spectroscopy that I'm sure is on some of your minds. So here's just an example of some work that I did with Joe Lama back in 2015, 2016, when we were interested in understanding this contamination from the solar surface or solar type activity. And what you can see on the left is that depending on how you simulate, in this case, it's a hot Jupiter simulated across actual SDO images of the sun at different rotational phases, you get a very different transmission. You get different transit. And when you do this for spectroscopy, it's then, of course, different for every resolution element. That's how we build up our transmission spectrum. So this is something that I think is really important in these papers. We've done it for all the SDO wavelengths and also for Lyman alpha. And so I encourage you to look there if you're interested in how one could mitigate this issue. And essentially the answer is lots and lots of transits. So we have to be prepared. When you get those proposals, you have to be prepared for multiple transits in order to get real radii at particular resolution elements. But of course, many of the exoplanets that we're most interested are these M stars. And these M stars, they're much smaller in mass, they're lower luminosity, and they are much more active, which means that they are more variable in these high energy wavelengths, in fact, at all wavelengths, but especially in the UV and the X-ray. And their habitable zones are much closer in. So as we start thinking about doing transmission spectroscopy of smaller and smaller planets in the habitable zones of these M stars, which are the first ones we are now looking for, trying to understand right now with JWST, getting down to the details of the stellar variability becomes really, really critical, both from the heating and chemically modifying perspective, but also then in the probing of the planetary atmosphere. And I just wanted to point this out for those who don't think about M dwarfs nearly as much as I do, is that when we say the word M dwarf, we really mean a huge range of stellar masses. They go all the way from 0.1 to about 0.8 solar masses and 3 orders of magnitude in luminosity. So they really span quite a wide range, but they are by far the dominant exoplanet hosts. So when we say we want to look around an average star like our sun, the reality is the sun is not average, and M stars are in fact average and make up about 75% of all the stars in our galaxy and are also the dominant planet host. So with the M star spectrum, so this is something that, with Arcus, you'll be interested in viewing, you'll see that there's very, very few X-ray and UV photons compared to the infrared, the red and the infrared, right? We call these red dwarfs for a reason. There's literally 1 million more red photons than there are to a UV photon. But of course, as we know, not every photon is equal, and these really high energy ones are super important to observe. So I'm glad that they're part of your science cases. And so the UV, for instance, as I said, can photochemically modify the lower atmosphere, and then the X-ray and the extreme UV can photodissociate atoms and be part of the photoevaporation process. And so if we are wondering whether or not rocky planets around M stars even have atmospheres to observe in the first place, we need to understand their X-ray and UV environment, because it's quite possible that in their first 300 to 500 million years, the atmospheres have been completely eroded by the star. So this is where a lot of these observations will come in handy. And then thinking long into the future, someone already mentioned as precursor science for the Habitable Worlds Observatory, here is an example, a modeled reflectance spectrum with a mission like Habitable Worlds Observatory of an Earth around an M star. And here is exactly the Earth's atmosphere, but showing up very differently depending on the input UV emission. And you could even have false positive biosignatures for those of us who are interested in looking for signs of life. For instance, here's the example of O3. The O3 biosignature is vastly different, not because there is or there isn't surface life on this, simulated planet, but because the UV input is completely different. So this is just really should drive the point home that we need to understand this better. Also with probing the upper atmospheres here, here's a plot made by Katja Poppenhager, but I found it in Scott Wilkes' 2019 Decadal Survey white paper, which nicely demonstrates how what we can do and probe, what we can do with X-ray or soft X-ray wavelengths here. You're now getting deeper transits, and you can get a transmission spectrum in the X-ray, which is very exciting and difficult and worth doing to probe completely currently unprobable layers of the atmosphere. Another thing we can do is, as I said, measure tails of of the evaporating gas, and we can do this with Lyman alpha. And from what I saw today in Kevin's talk, you guys are going to be able to get Lyman alpha, so this is really great. You can do transmission spectroscopy with Lyman alpha from the test-like orbit. It will be even better than what we can do with HST, so I think that is fabulous. And this will be directly measuring the potential photoevaporation, and that would help answer a very important question right now in our field of, do planets form or evolve into the two populations that we currently observe? We see that small planets come in two sizes through this bimodal. You can see this bimodal plot here discovered by Kepler. And lastly, since I see that I'm over time, I just wanted to say that we do also detect a ton of flares. I'm not going to talk about flares because I know Rachel Austin is going to talk tomorrow about flares, but this is one, I would consider this low-hanging fruit in the X-ray far UV domain, where these M stars pop off pretty regularly, much stronger than we anticipated, and absolutely will be, you'll get a pile of them and do great statistics there. So to conclude, I only talked about these top few things that X-ray and UV observations could do. We could study planet atmospheric escape. We could study planet photochemistry, stellar flares, of course. And then there's a whole list of other stuff that I didn't have time to talk about, but I'd love to chat with anyone who's interested. Thank you.
Thank you for an excellent talk. I think we've got time for a question if anybody would like to pose one. Laura. No, Laura's clapping, sorry.
I didn't hear your banging wine glass, John, if you did.
I'll be louder and more obnoxious next
time. Evgenya, just a general question. How important do you think the simultaneity of getting the soft X-rays and the UV is going to be here? Is there any particular advantage there, or would it matter very much if we had multiple band passes in, say, the UV?
I think having the simultaneous can only help. It can help in a few ways. One is in characterizing flares in general, and no doubt Rachel will talk about that in detail tomorrow. So we can characterize different lines at different formation temperatures. It can also help in the sense from the planet transmission spectroscopy perspective as being an internal, what I call a flareometer, right? So if you're looking for, let's say you have true absorption, some sort of absorption, say in oxygen, and you want to be sure that it's not the star varying, you will have other variability diagnostics in your complete X-ray to far UV spectrum, right? That you can kind of monitor the star simultaneously as you're trying to observe the planet. And I think that will be very powerful.
Okay.
I think for sure. I think simultaneity is going to be a powerful thing for you.
Great. Thank you.
That's great.